Imagine for a second that you are holding a standard pocket-sized matchbox in the palm of your hand.
Just a regular little cardboard box.
Yeah, exactly.
Yeah.
It is light, right. It's just a little cardboard and wood.
Barely weighs anything.
Right. But now, I want you to imagine that same matchbox taking up the exact same amount of physical space in your hand, but it weighs as much as an adult elephant.
Which is, what, like several tons?
Yeah, thousands of pounds. Your hand would instantly shatter.
Oh, absolutely.
The matchbox would plunge straight through the floorboards. It would punch right through the foundation of your building.
It would just keep going.
Right. It would likely burrow deep into the Earth's crust, purely driven by its own incomprehensible density.
Because the sheer mass is concentrated in such a tiny area.
Exactly. And today, for you, the listener, we are going to explore exactly how an object like that actually gets forged in the violent death of a star.
It is a wild process.
It really is. But to even begin to understand a concept that extreme, I feel like we first have to grapple with the ultimate paradox of the science that actually found it.
Yeah, it is a fundamental paradox, because when you think of a traditional scientific discipline, you usually think of tangibility.
Like you can touch the stuff you're studying.
Right. A biologist isolates a cell on a glass slide, stains it, and physically manipulates it.
Or a chemist mixes compounds in a beaker to watch a reactive physical change.
Exactly. Even an engineer tests the sheer strength of a steel beam by physically applying pressure to it until it snaps. There is this tactile, hands-on feedback loop.
You can touch the laboratory.
Yes.
But step into the world of astronomy, and that physical laboratory completely vanishes.
It is gone.
You are suddenly navigating this scientific landscape where it's physically impossible to touch what you study.
We are dealing with an entire field of human knowledge. I mean, everything we know about the origin of the universe, black holes, the life cycles of stars, alien planets.
And it all relies entirely, like 100%, on simply intercepting ancient light.
It is the purest form of observational science.
Because we cannot just go there.
Right. I mean, aside from a handful of space probes we have managed to fling into our immediate solar neighborhood, and maybe some lunar dust we physically brought back.
A very small amount of dust.
Very small. But the overwhelming majority of professional astronomy is conducted across these vast, incomprehensible distances.
We cannot tweak the variables of a star to see what happens.
No, we cannot fly out to a nebula to take a core sample. We are entirely at the mercy of the photons that just happen to reach us.
Which is exactly why we are doing this deep dive today. We are going on a journey to unpack how we pull these massive cosmic secrets out of the dark.
It is a lot of forensic work.
It is. We are going to start by exploring the incredible and honestly sometimes wonderfully bizarre tools that humans have engineered to capture this light.
Both from down here on the ground and up in the vacuum of space.
Right. And then we are going to take those tools and point them. First, we will look right next door at our highly toxic planetary neighbor, Venus.
Just to see planetary physics operating at its absolute most brutal extreme.
Yeah, and from there we will push out into deep space. We will examine the highly complex, vividly colorful deaths of stars.
And finally, we'll look closely at the crushed, glowing embers they leave behind.
Which brings us right back to that impossibly heavy matchbox.
It really is staggering when you think about it.
The idea that all of this grand cosmological theory comes purely from logging light.
Yeah, it is forensic science on a galactic scale.
You are analyzing the faint smear of a photon on a digital sensor and somehow reverse engineering the lifespan of an entire galaxy.
But doing that requires an eye far superior to our own. I mean, modern astronomy is no longer a solitary figure shivering on a mountaintop, squinting through little glass eyepiece.
Right, it is massive now.
It is a highly mechanized endeavor. It is about intercepting invisible radiations across the entire electromagnetic spectrum.
And interpreting just petabytes of digital data.
Exactly. And fundamentally, waging a constant engineering war against the physical limitations of our own planet's atmosphere.
So to truly understand the cosmos, we first have to understand the evolution of the eye we use to observe it.
And the story of that eye usually invokes the image of Galileo Galilei in the early 1600s.
Though I think it is a massive historical misconception that he actually invented the telescope.
Oh, yeah, that is a big myth. The actual invention is generally credited to Dutch eyeglass makers around 1608.
Guys like Hans Lippershey, right?
That is right. They realized that by holding a convex lens and a concave lens at a specific distance from each other inside a tube, distant objects appeared closer.
But they mostly used it for boats.
Yeah, it was essentially treated as a novelty or a military tool for spotting ships on the horizon.
So what Galileo did in 1609 was realize the scientific potential of this tube,
He taught himself how to grind and polish his own lenses.
which drastically improved the magnification, right? From like 3 times to 20 or 30 times.
Exactly. And then, crucially, he took this maritime spyglass and aimed it straight up.
And that simple upward pivot just shattered the prevailing cosmological paradigm.
It really did. The Aristotelian view, which had dominated for centuries, held that the heavens were perfect, unchanging, and revolving entirely around the Earth.
But Galileo's lenses revealed a universe that was messy, dynamic, and distinctly non-Earth-centric.
He looked at the moon and saw that it was not a perfect pearlescent sphere.
It was scarred with jagged craters and immense mountain ranges.
He pointed it at Jupiter and tracked 4 tiny points of light moving around it night after night.
Proving that not everything in the universe orbited the Earth.
Yeah.
Jupiter had its own center of gravity.
Right. And he looked at the cloudy band of the Milky Way and resolved it into thousands of individual, distinct stars.
But arguably, his most consequential observation involved Venus.
Yes. When Galileo observed Venus over a period of months, he saw that it went through phases, exactly like our moon.
He would go from a thin crescent to a half disk to a small, fully illuminated disk.
I want to break down why that is so important, because it is just a brilliant piece of deductive reasoning.
Yeah, let us get into that. Under the old Ptolemaic model, where everything orbited the Earth, Venus was thought to orbit between the Earth and the Sun.
If that were true, we would only ever see the dark side of Venus.
Or maybe a slight crescent.
Right, because the sun would always be behind it from our perspective.
Exactly. The only geometric way for Venus to display a full cycle of phases, especially a full Venus where the entire disk is eliminated, is if Venus is orbiting the Sun.
And eventually passing on the far side of the sun relative to Earth.
That observation alone was the definitive empirical nail in the coffin for the Earth-centered universe.
It was undeniable proof.
But here's what I find so fascinating about Galileo's setup. As brilliant as he was, and as revolutionary as these discoveries were, the physical tool he was using was profoundly flawed.
Oh, deeply flawed.
There is a famous historical anecdote from 1610. Galileo points his newly improved telescope at Saturn.
Right.
Now, we know Saturn has this magnificent sweeping ring system, but Galileo's lenses simply were not sharp enough to resolve the rings as separate from the planet.
The image he saw was blurry and highly distorted. He could not quite make out what the protrusions were.
So he hypothesized that Saturn was a triple planet system.
Or that it had 2 very large immobile moons affixed to its sides. In his notes, he literally referred to them as ears.
Ears.
Yeah, he drew sketches of a central sphere with 2 handle-like appendages on either side.
The father of observational astronomy, looking at the second largest planet in the solar system and declaring it the planet with ears.
It is pretty funny in retrospect.
It wasn't until almost half a century later, in 1655, that Christian Huygens, using a much better, much longer telescope, recognized them as a flat ring system not touching the planet.
And then in 1675, Giovanni Cassini found the dark gap within the rings.
Which we still call the Cassini division today.
Right.
But this brings up a fundamental physics problem. Galileo, Huygens, Cassini, they were all using refracting telescopes. Telescopes that use glass lenses to bend light.
Correct.
Now, lenses work perfectly fine for eyeglasses or a magnifying glass. So why did the scientific community eventually abandon them for large-scale astronomy?
Oh.
If you want to see deeper into space, why not just cast a monolithic gargantuan glass lens?
It comes down to the inherent physical properties of light and glass. The problem you were describing is known as chromatic aberration.
Or color fringing, right?
Exactly. When starlight, which is white light containing all the colors of the spectrum, enters a curved glass lens, the glass slows the light down and bends it toward a focal point.
But refraction is not uniform across all wavelengths.
No, it is the prism effect. A lens is essentially just a circular prism. Different colors of light have different wavelengths, and therefore they bend at slightly different angles when they hit the glass.
So blue light, having a shorter wavelength, bends more sharply than red light.
Right, because red light has a longer wavelength. So the different colors do not all arrive at the same destination.
When the light exits the back of the lens, the blue light reaches its focal point slightly closer to the lens,
while the red light focuses slightly farther away.
So as an observer, when you put your eye up to the eyepiece to look at a star, You cannot focus on all the colors simultaneously.
If you tune the telescope to focus on the red light, the blue light is out of focus and vice versa.
The result is that every star, every planet, looks like a blurry smear surrounded by a highly distracting, rainbow-colored halo.
Which is an absolute nightmare if you are trying to measure the exact position of a star or analyze the crisp edge of a planetary crater.
Now, I know telescope makers tried to fix this by adding a second, concave corrective lens made of a different type of glass.
Yeah, they were trying to force the colors back together into a single focal point.
But even with those achromatic lenses, there is a hard physical ceiling to how big you can build a refractor.
A very hard ceiling, and it is dictated by gravity. Glass is incredibly dense and heavy.
Because a telescope lens requires light to pass completely through it, you cannot put anything behind the lens to hold it up.
Exactly. You can only physically support the glass around its incredibly thin, fragile outer edge.
So if you try to cast a lens that is, say, 4 feet across, and you mount it in a tube holding only the rim,
The sheer immense weight of the glass will cause the center of the lens to sag and warp under the pull of Earth's gravity.
even a microscopic sag completely ruins the optical precision.
The light bends incorrectly and the telescope becomes useless. The largest refracting telescope ever built is the Yerkes Observatory Telescope in Wisconsin, completed in 1897.
And its lens is 40 inches across.
That is the absolute maximum limit. Any larger and the glass deforms itself.
So astronomy hit a wall. If we wanted to see deeper, we needed bigger eyes, but physics said glass lenses could not get any bigger.
The solution to this did not come from better glass. It came from Isaac Newton completely throwing out the concept of a lens.
In 1668, Newton analyzed the chromatic aberration problem and realized that as long as light passes through a medium like glass, it will separate into colors.
His brilliant circumvention was to build a telescope that collected light by bouncing it off a highly polished, curved surface instead.
The invention of the reflecting telescope.
And he didn't use glass for his mirror, did he?
No, the technology to coat glass with reflective silver or aluminum just did not exist yet,
Newton built his mirror out of a solid metal alloy called speculum metal.
which was a highly toxic mixture of copper, tin, and arsenic.
It was difficult to cast and tarnished quickly, requiring constant repolishing, but optically it was a revelation.
Because it solved the color problem instantly. When light bounces off a mirrored surface, it does not matter if it is red light, blue light, or green light.
The law of reflection applies equally to all wavelengths.
They all bounce off at the exact same angle and arrive at a single crisp focal point. No more rainbow halos.
And crucially, it solved the gravity problem. Because the light only hits the front surface of the mirror and bounces back, the back of the mirror is optically irrelevant.
Meaning you can put whatever you want behind it.
Exactly. You can support the entire back of the mirror with a massive, rigid steel framework. You aren't just holding it by the edges anymore.
Because you can support it from behind, the structural limit disappears.
You can theoretically build a mirror as large as your engineering capabilities allow. Reflectors won the evolutionary race of telescopes because they are scalable.
And when you look at how we have scaled them today, the engineering is almost difficult to comprehend.
We have come a long way from Newton polishing a toxic copper arsenic disc.
Modern observatory mirrors are masterpieces of material science. They aren't even made of standard glass anymore.
They use specialized low-expansion glass ceramics. They have to use those materials because standard glass expands and contracts as the ambient temperature changes throughout the night.
If a massive telescope mirror expands even a fraction of a millimeter as the night air cools, the curvature changes, and the image goes out of focus.
Low-expansion ceramics are designed to hold their exact shape regardless of thermal fluctuations.
And the casting process for these mirrors is an event in itself. They melt chunks of this specialized glass in a spinning circular furnace,
The rotation forces the molten glass to wash up against the sides of the mold,
naturally forming a parabolic curve.
which saves them from having to grind away tons of solid glass later, but then they have to cool it.
They cannot just turn the oven off. If the outside cools faster than the inside, the stress will shatter the entire mirror.
They have to lower the temperature by a fraction of a degree every day. It can take up to 6 months just to cool the glass down to room temperature safely.
And that is just the beginning. Once it cools, it undergoes a polishing process that can take well over a year.
The surface of the mirror must be flawlessly, unfathomably smooth. Because remember, what we are trying to do, we are trying to bounce photons that have traveled for billions of years and force them to converge perfectly.
If the mirror has microscopic ridges or bumps, those photons scatter.
Let us put some numbers to this, because this is where my mind was truly blown. Let us look at the Gemini Observatory.
There are two identical telescopes, right? Gemini North in Hawaii and Gemini South in Chile.
They each use a single monolithic primary mirror that is 26.2 feet across. That is an 8-meter piece of glass.
That mirror is polished to an accuracy of 16 nanometers, 16 billionths of a meter.
To contextualize that level of precision, you have to realize that they are polishing the surface down to the scale of individual molecules.
If the curvature is off by even a fraction of the wavelength of the light it is trying to capture, the image of a distant galaxy will be fundamentally blurred.
Here is the analogy that makes this stick. If you took that 26-foot Gemini mirror and you magically scaled it up so that it was the exact same diameter as the entire Earth, nearly 8,000 miles across.
Okay, wow.
If you scaled up the imperfections along with it, the absolute highest bump, the tallest mountain on that Earth-sized mirror, would be roughly 12 inches high.
A planetary-sized object with a maximum topographic variation of 1 single foot.
It is an almost perfect geometric surface.
When you combine that flawless curve with a micro-thin, vacuum-applied coating of pure aluminum, you create an instrument capable of capturing light from celestial objects that are 500 million times fainter than what the naked human eye can detect.
It is a triumph of engineering.
So we conquered the lens problem. We figured out how to cast and polish these gargantuan 26-foot ultra-precise mirrors. But
we are still building them on Earth.
Which means we still have a massive turbulent ocean of gas right in front of our faces.
The atmosphere, the great nemesis of observational astronomy.
When you look up at a star at night and see it twinkling, it looks beautiful and romantic.
Yeah.
But to an astronomer, that twinkling is a disaster.
It is optical distortion.
The starlight has traveled in a perfectly straight line through the vacuum of space for millions of years, totally undisturbed.
But in the final microsecond of its journey, it hits Earth's atmosphere. It has to pass through miles of moving air currents, temperature gradients, and turbulent wind shears.
The atmosphere acts like a constantly shifting, chaotic lens. The starlight is refracted slightly left, then slightly right, rapidly oscillating.
This is what we call atmospheric seeing. Even if you have a perfectly engineered 26-foot mirror, if you place it at the bottom of our atmosphere, it is like trying to read the fine print on a coin sitting at the bottom of a fast-flowing, rippling swimming pool.
The image is constantly jumping and smearing.
So how do we fight back? How do ground-based telescopes overcome the very sky they are looking through?
Because you cannot just build a 50-foot solid glass mirror. We hit another limit there.
Even with rear structural support, once a piece of glass gets wider than about 26 feet, its sheer mass becomes unmanageable.
It is too heavy to truck up a mountain.
And as a telescope tilts to track a star, gravity pulls on it differently, causing the massive disk to slightly flex and lose its perfect 16-nanometer polish.
So if physics prevents you from casting a single piece of glass larger than 8 meters, you have to rethink the architecture entirely.
You have to cheat. Instead of one massive mirror, you build a segmented mirror.
Which brings us to the W.M. Keck Observatory in Hawaii, completed in 1992. It completely revolutionized telescope design.
Keck does not use a single mirror. It uses 36 individual, relatively thin, hexagonal mirrors.
They're fitted closely together, like honeycomb tiles, to act in unison. Combined, they create a light-gathering surface that is 33 feet or 10 meters across.
But segmenting the mirror introduces a monumental new problem. You cannot just bolt 36 mirrors to a steel frame and expect them to stay perfectly aligned.
The telescope is constantly rotating to track the sky.
As it moves, gravity pulls on the frame from different angles, causing microscopic sagging. The ambient temperature shifts. The wind blowing across the open observatory dome physically shakes the structure.
If those 36 segments fall out of alignment by even a few nanometers, you do not have a 10-meter telescope. You have 36 blurry, overlapping, out-of-focus images.
Enter the technology that essentially saved ground-based astronomy: active optics.
To keep these segments perfectly aligned, they aren't statically bolted down. Every single one of those 36 hexagonal tiles is mounted on a series of computer-controlled actuators.
Tiny, ultra-precise motorized pistons.
Exactly. The telescope uses a series of sensors to constantly monitor the alignment of the segments. It calculates the exact amount of gravitational sag, the thermal expansion of the steel, the pressure of the wind.
And then a computer fires commands to those motorized pistons to physically push, pull, and tilt every individual mirror segment to correct the alignment.
And it does this twice every single second.
And the precision of those adjustments is staggering. The pistons are moving the mirrors by microscopic fractions of a millimeter adjustments, 1,000 times finer than the width of a human hair.
It is like having a high-end sports car with an active suspension system.
That is a great comparison.
As the car drives over a bumpy road, sensors read the terrain, and the suspension instantly absorbs the impact. It drops a wheel into a pothole and raises it back out so fast that the driver's cup of coffee does not even ripple.
The car's chassis stays perfectly level.
Active optics does exactly that, but for optical distortions. It actively wrestles with gravity and wind in real time to force those 36 separate pieces of glass to behave mathematically like one single, rigid, unchanging parabolic surface.
It is brilliant, and it proved so successful that the segmented, actively controlled design became the blueprint for the modern megatelescope era.
Look at the Very Large Telescope, the VLT, operated by the European Southern Observatory in the high-altitude Atacama Desert of Chile.
It isn't just one telescope. It is an array of 4 enormous, individual 27-foot telescopes.
I love their names. They are named in the local indigenous Mapuche language: Antu, Quayen, Melipal, and Yupin.
The Sun, the Moon, the Southern Cross, and Venus.
Most nights, they operate independently, gazing at different targets. But the true power of the VLT is interferometry.
Using a complex underground network of mirrors and perfectly calibrated light tunnels, astronomers can combine the light from all 4 telescopes simultaneously.
When synced up perfectly, they achieve the resolving power, the ability to see fine detail of a single telescope mirror over 400 feet across.
And we are currently building even bigger. The giant Magellan telescope, also under construction in Chile.
This one uses a different segmenting approach. Instead of 36 small hexagons, it will use 7 massive, circular 27-foot mirrors arranged like a daisy flower.
When you combine the light from those 7 enormous mirrors, it will have the resolving power of a single 70-foot dish.
The projections claim it will produce images 10 times sharper than the Hubble Space Telescope.
Which is an audacious claim. Beating a space telescope from the ground means you have completely mastered active optics, and you are using adaptive optics.
Shooting lasers into the sky to measure atmospheric turbulence.
And deforming secondary mirrors thousands of times a second to cancel out the twinkle of the stars.
Before we officially leave the ground and head into space, we have to talk about one specific ground-based telescope, because it sounds like pure science fiction.
Oh, the Large Zenith Telescope in British Columbia, Canada.
It boasts a massive 20-foot primary mirror. But the mirror isn't made of low-expansion glass, and it isn't polished for a year.
The mirror is a spinning vat of liquid mercury.
Liquid mirror telescopes. They seem absurd on their face, but the underlying physics are incredibly elegant.
Let us unpack how a liquid can act as a precision optical instrument.
It relies entirely on fluid dynamics and rotational physics.
If you have a pan of liquid, its surface naturally settles completely flat due to gravity. But if you take that pan and spin it at a perfectly constant speed, centrifugal force pushes the liquid outward toward the edges.
Because the liquid is constrained by the walls of the pan, it has nowhere to go but up.
So the edges rise and the center dips.
Exactly. And the geometry of physics dictates that the resulting shape of that spinning fluid surface is a perfect mathematical parabola.
A parabola happens to be the exact, precise curve required to bring parallel rays of starlight to a single focal point.
So instead of spending billions of dollars casting glass and polishing it to nanometer precision for a decade, you just take a large, shallow dish, fill it with a pool of highly reflective, highly toxic liquid mercury, and spin it with an electric motor.
The rotation naturally, flawlessly shapes the surface into a perfect 20-foot mirror. The surface is so smooth because it is a liquid, it naturally heals any microscopic imperfections.
It is remarkably cost-effective. You can build a massive observatory for a fraction of the cost of a traditional glass mirror. But, as with all engineering, there is a severe limitation.
You cannot tilt it.
Precisely. If you want to point a standard telescope at a star on the horizon, you tilt the tube.
If you try to tilt a spinning pool of liquid mercury, the mercury immediately sloshes over the side, ruins the mirror, and creates a massive toxic hazard.
A liquid mirror telescope can only ever point straight up at the zenith.
Hence the name, Large Zenith Telescope. You just point it straight up, turn on the motor, and let the Earth's rotation slowly drag the sky across your field of view.
You can only study exactly what happens to pass directly over your head. It is a brilliant, highly specialized tool.
But ultimately, whether you are using active optics, lasers, or spinning liquid metal, you are still fighting the atmosphere.
You're still trying to look through the swimming pool. If you want absolute, unobstructed clarity, you have to leave the pool entirely.
You have to put the eye above the clouds, the era of the space telescope.
And this wasn't a sudden idea. The theoretical concept predates the space age entirely. In 1946, an American astrophysicist named Lyman Spitzer wrote a paper proposing the scientific benefits of an extraterrestrial observatory.
Let's remember the historical context here. 1946, World War II had just ended. We hadn't even put a satellite into orbit.
Sputnik was still 11 years away.
The concept of human spaceflight was pure science fiction, and Spitzer's already doing the math on how a telescope orbiting in a vacuum would revolutionize physics because it wouldn't have to deal with atmospheric seeing.
It was a visionary proposal, but it took decades of technological advancement, political lobbying, and immense funding to make it a reality.
Finally, in April 1990, the Space Shuttle Discovery carried the Hubble Space Telescope into low Earth orbit.
It was a $1.5 billion marvel of engineering, placed into an orbit roughly 380 miles above the Earth's surface, traveling at a staggering 17,200 miles per hour.
When you think about the physical mechanics of Hubble, you realize how alien its operating environment is. Down on Earth, a massive telescope is anchored to tons of concrete embedded in a bedrock mountain.
It plugs into a local power grid.
But Hubble is untethered. It operates in freefall, in a hard vacuum, experiencing massive temperature swings as it passes from the searing heat of direct sunlight into the freezing shadow of the Earth every 90 minutes.
Which means it has to be entirely self-sufficient. Power is generated by two massive solar panels stretching almost 40 feet across,
Converting sunlight directly into electricity to run the computers and scientific instruments.
and charging onboard batteries for when it passes through Earth's shadow.
But the pointing mechanism is what really blows my mind, because if you want to point Hubble at a specific distant galaxy, you cannot just fire a rocket thruster to turn the telescope.
No, absolutely not. Rocket thrusters emit exhaust gases, propellants, unburned hydrocarbons, water vapor.
In the vacuum of space, those gases would immediately form a cloud around the telescope, freezing onto the delicate optics and completely blinding the sensors.
You have to move the telescope without emitting a single molecule of exhaust.
So they use reaction wheels. This is pure Newtonian physics at work, the conservation of angular momentum.
Imagine you are sitting in a swiveling office chair with your feet off the ground. You are holding a heavy bicycle wheel by its axle, and the wheel is spinning rapidly.
If you physically twist that spinning wheel to the left, the rotational force reacts against you, and your office chair will spin to the right.
Every action has an equal and opposite reaction.
Hubble uses this exact principle. Inside the spacecraft, there are heavy, motorized wheels mounted on different axes.
When the onboard computer wants to rotate the massive 12-ton telescope to point at a new target, it simply uses an electric motor to spin one of those internal wheels in the opposite direction.
The wheel spins clockwise, the telescope slowly rotates counterclockwise.
And once it reaches the target, it spins the wheel the other way to brake and stop the rotation. It is silent, exhaust-free movement.
But getting to the target isn't enough. Many of Hubble's most profound images require exposure times lasting hours or even days to gather enough faint photons.
The telescope must remain locked onto its target with microscopic stability while hurtling around the Earth at 17,000 miles per hour.
To achieve this, it uses fine guidance sensors. These sensors lock onto specific, known guide stars near the target area.
They monitor the position of these stars constantly. If the telescope drifts by even a fraction of a millimeter, the sensors instantly detect the movement.
Tell the reaction wheels to adjust their speed and nudge the telescope perfectly back into place.
It is an engineering masterpiece. But we cannot talk about Hubble without talking about the disaster.
The most public, embarrassing, and heart-stopping failure in astronomical history.
1990. Hubble launches. Decades of work, billions of dollars. The world waits with bated breath for the first images from the ultimate eye in the sky.
It opens its protective aperture door, the light floods in, the sensors capture the first image, they beam it back to Earth.
It is blurry.
It was a devastating realization. The entire point of spending $1.5 billion to put a telescope in space was to achieve crystalline, perfect clarity.
And the images were fuzzy, marred by a halo of unfocused light.
It didn't take long for engineers to diagnose the problem. The 8-foot primary mirror, which had been painstakingly polished on Earth for years, had been ground to the wrong shape.
And when we say wrong shape, we aren't talking about a massive dent.
We are talking about an error of roughly 1/50th the thickness of a human hair. The mirror was too flat near the edges.
But in optics, an error of a few hundred nanometers is catastrophic. Because the edges were too flat, the light bouncing off the outer rim of the mirror focused at a slightly different point than the light bouncing off the center.
It is a flaw called spherical aberration. Ironically, it is a very similar effect to the chromatic aberration Galileo fought, just caused by a different physical mechanism.
Hubble was nearsighted. It could not focus light to a sharp point.
Fortunately, Hubble had been deliberately designed with modularity in mind. It was meant to be visited and upgraded by astronauts in the space shuttle.
So NASA spent 3 years developing a fix. And the fix is a fascinating piece of lateral engineering. You cannot just fly up and replace the massive 8-foot primary mirror. It is the structural heart of the telescope.
You have to fix the light after it bounces off the flawed mirror, but before it hits the cameras.
Exactly. In 1993, the Space Shuttle Endeavour launched on one of the most complex, high-stakes orbital missions ever attempted.
Astronauts conducted 5 exhausting spacewalks. They removed an older instrument to make room, and they installed a device called COSTAR, the Corrective Optics Space Telescope Axial Replacement.
Which is essentially a set of contact lenses for a space telescope.
That is a great analogy. COSTAR contained a series of tiny coin-sized mirrors. These mirrors were deliberately polished to have the exact opposite flaw of the main mirror.
They were deformed precisely to cancel out the spherical aberration.
When the light bounced off the flawed primary mirror, it was directed into COSTAR. The corrective mirrors warped the light back into perfect alignment and then fed it into the scientific instruments.
The drama of that mission is unparalleled. Floating in the hard vacuum of space, locked in a bulky pressurized suit where you can barely bend your fingers, moving multi-ton instruments into tight slots on a machine hurtling through the dark at 5 miles a second.
But it worked. They essentially performed microscopic eye surgery on a satellite.
And once those corrective mirrors were in place, the universe snapped into breathtaking focus.
And the scientific return on that investment fundamentally changed cosmology. We can trace so many modern astronomical paradigms directly back to Hubble's newly corrected optics.
Let us run through a few of the massive milestones. In 1992, even before the fix, using the sharper center of its vision, Hubble found a massive disk of gas whipping around the center of the galaxy M87 at immense speeds.
It was the first definitive observational evidence proving the existence of supermassive black holes at the hearts of galaxies.
In 1994, it provided a front-row seat to planetary physics in action. It watched as the fragmented comet Shoemaker-Levy 9 slammed into the atmosphere of Jupiter, leaving massive, Earth-sized dark impact scars in the gas giant's clouds.
We watched a planetary collision in real time.
Then in 1995, we got the photograph that ended up on the front page of every newspaper, magazine, and science textbook in the world. The Pillars of Creation.
Hubble pointed its cameras at the Eagle Nebula and captured these towering, light-years-long columns of cold interstellar gas and dust.
It showed us the active stellar nurseries where gravity is currently crushing gas down to ignite brand new stars. It was a perfect synthesis of profound science and profound art.
And cosmologically, its most significant contribution came in 2001. Astronomers used Hubble to precisely measure the brightness of specific, distant supernovas, exploding stars, acting as cosmic distance markers.
By comparing how far away they were with how fast they were receding, Hubble provided the crucial data, proving that the expansion of the universe isn't slowing down due to gravity.
It is accelerating. The universe is flying apart faster and faster, driven by a mysterious force we now call dark energy.
It rewrote the physics textbooks. But for all of Hubble's glory, visible light, the optical spectrum that human eyes can see and that Hubble primarily captures is only a tiny fraction of the cosmic story.
It is a very narrow window. The universe emits energy across the entire electromagnetic spectrum, from high-energy gamma rays and X-rays down to low-energy microwaves and radio waves.
If we only look at the visible light, we're essentially walking into a symphony orchestra with earmuffs that only let us hear the violins.
We miss the cellos, the brass, the percussion. To get the full picture of the cosmos, we had to develop invisible astronomies.
And the one we need to focus on to transition into our next topic is infrared astronomy. Infrared is fundamentally heat radiation.
It has a longer wavelength than visible red light, so our eyes cannot detect it, but our skin can feel it as warmth.
Why is an infrared telescope so crucial for looking at space?
Because the universe is incredibly dusty. The space between stars isn't entirely empty. It is filled with immense, drifting clouds of microscopic interstellar dust silicates, carbon molecules, frozen gases.
When visible starlight tries to pass through these clouds, the short wavelength visible photons crash into the dust particles and scatter.
The light gets completely blocked. To a visible light telescope like Hubble, a dense dust cloud just looks like a dark, opaque wall. We cannot see what is inside or behind it.
But infrared light has a longer wavelength. It is essentially wider than the dust particles.
Exactly. Because the waves are longer, they do not crash into the microscopic dust. They slip right past it.
Infrared light passes completely through these dense nebulas as if the dust wasn't even there.
By building sensors that detect infrared heat rather than visible light, we can pierce the veil. We can look deep inside those opaque, dark clouds and see the infant stars glowing warmly as they are being born.
The engineering required to capture infrared is intensely difficult, though, because heat is the enemy of the telescope itself.
Our sources mention a pioneering mission from 1983 called IRAS, the Infrared Astronomical Satellite.
If you put an infrared sensor in space, the electronics of the satellite itself generate heat. The metal frame absorbing sunlight generates heat.
If the telescope is warm, the infrared sensor will just be blinded by the telescope's own thermal glow. It is like trying to see a dim flashlight on a distant hill while someone is shining a bright floodlight directly into your eyes.
To see the faint infrared glow of a distant star, the telescope itself has to be incredibly cold.
So, to solve this, the IRS engineers basically built a flying thermos. They wrapped the entire telescope in a massive cooling jacket filled with liquid helium, driving the temperature of the instrument down to near absolute zero.
It worked flawlessly, but it gave the telescope a strict expiration date. The liquid helium slowly cooled off into space as it absorbed the ambient heat.
IRAS mapped 98% of the entire sky in infrared over the course of 300 days.
But once that coolant tank ran dry, the telescope warmed up, the sensors blinded themselves with their own heat, and the mission was over.
Which laid the groundwork for the true successor to Hubble, the James Webb Space Telescope.
JWST takes everything we have learned and pushes it to the extreme. It is an infrared observatory. But instead of just using a finite tank of liquid helium, it actively protects itself.
It is parked almost 1 million miles away from Earth, far beyond the moon's orbit, at a gravitationally stable point called L2.
And it utilizes a massive 5-layer sun shield, the size of a tennis court, to permanently block the heat of the sun, Earth, and moon.
This passive cooling allows its mirrors and sensors to sit at roughly minus 390 degrees Fahrenheit indefinitely.
And the mirror itself is a marvel. Borrowing the segmented active optics lessons from ground-based telescopes like Keck, JWST doesn't have a single solid mirror.
It has a 21-foot mirror comprised of 18 gold-coated hexagonal beryllium segments.
Gold is used because it is one of the most efficient reflectors of infrared light. It had to be folded up like origami to fit inside the launch rocket and then perfectly unfurl and align itself in deep space to nanometer precision.
So we have built these miraculous machines. We have circumvented atmospheric seeing. We have compensated for thermal expansion. We have tapped into invisible spectrums to pierce through obscuring dust.
The obvious question now is, what do we point them at?
Exactly. What does this massive accumulation of technological prowess actually reveal?
Before we push out into the deep cosmic structures, I want to point these tools right next door, because right in our own solar system is a planet that perfectly illustrates how crucial these invisible astronomies are.
We're talking about the second planet from the sun, Venus.
For centuries, before radar and infrared astronomy, Venus was a blank canvas. When you look at Venus through a standard optical telescope, even a powerful one, you don't see a surface.
You just see a featureless, brilliantly white, highly reflective sphere.
It is completely shrouded in a permanent, unbroken layer of clouds. Because we could not see the surface, astronomers historically let their imaginations run wild.
Because Venus is closer to the sun, they assumed it was warmer than Earth. The clouds suggested immense humidity.
So for a long time, the prevailing theory was that Venus was a swamp planet, a prehistoric, tropical jungle world, perhaps teeming with alien dinosaurs or lush vegetation beneath the clouds.
It was a romantic notion, born entirely from the limitations of optical astronomy. But when we finally developed the tools to pierce that veil, when we bounced radio waves off the surface to map the topography, and used infrared sensors to measure the thermal radiation baking out from beneath the clouds, that tropical fantasy instantly evaporated.
We discovered an absolute nightmare. Earth's twisted sister.
It is a tragedy, really, because when you look at the raw physical data, Venus and Earth look like twins on paper.
Venus is a rocky terrestrial planet. It is almost exactly the same diameter and mass as Earth.
The internal structure is functionally identical. It has a dense core made of iron and nickel. It has a thick, rocky mantle and a solid silicate crust.
If you were building a planet from a blueprint, Earth and Venus are the same model.
But the environment is the exact opposite of a tropical paradise. Venus is the hottest planet in the entire solar system.
Which is deeply counterintuitive for most people.
Right, because Mercury is right there. Mercury is the closest planet to the sun. It is literally skimming the solar atmosphere.
It is a common trap to assume proximity to the nuclear furnace equals maximum heat, which is why Mercury seems like the obvious candidate for hottest planet.
But Venus utterly shatters that logic through sheer atmospheric oppression.
Mercury has practically no atmosphere. It is just bare rock baking in the sun. The side facing the sun is scorching, but the heat immediately radiates away into space on the dark side.
Venus, however, is insulated. The extreme lead-melting surface temperature of Venus, which hovers around 900 degrees Fahrenheit or 475 degrees Celsius day and night, pole to equator is entirely dictated by the chemical composition of its atmosphere.
It is the ultimate cautionary tale of a runaway greenhouse effect. The atmosphere of Venus is incredibly thick and incredibly toxic.
It is composed of 96.5% carbon dioxide, with the remaining 3.5% being mostly nitrogen. There are clouds made of highly corrosive sulfuric acid.
To understand why it is so hot, you have to understand the molecular mechanics of carbon dioxide. CO2 is a greenhouse gas, which means it behaves selectively depending on the wavelength of light interacting with it.
Visible light from the sun, the short wavelength energy passes relatively easily through the carbon dioxide atmosphere. It travels down and strikes the rocky surface of Venus, warming the rocks.
Just like sunlight shining through the glass windows of a greenhouse, warming the soil inside.
Exactly. Now, the warm rocks trying to shed that heat, they radiate the energy back upward away from the surface. But they don't radiate it as visible light, they radiate it as thermal infrared energy.
And this is where the trap snaps shut. Infrared energy has a longer wavelength. The carbon dioxide molecules in the atmosphere resonate with that specific longer wavelength. They absorb the infrared heat. They are opaque to it.
The heat cannot escape back into space. The carbon dioxide absorbs the heat and then re-radiates it, sending much of it right back down to the surface, baking it further.
It is an infinite feedback loop. The surface gets hotter, baking more trapped gases out of the rocks, thickening the atmosphere, trapping even more heat.
It is a runaway train that ended with a planetary surface hot enough to melt solid lead.
And the heat is only one aspect of the hostility. Because there is so much gas trapped in that atmosphere, the physical mass of the air itself is crushing.
The atmospheric pressure at the surface of Venus is roughly 90 times greater than the pressure at sea level here on Earth.
90 times. To experience that kind of pressure on Earth, you would have to dive about 3,000 feet deep into the ocean.
If you stood on the surface of Venus, the sheer weight of the atmosphere would crush you like an aluminum can. Assuming the 900-degree heat didn't incinerate you first, or the sulfuric acid rain didn't dissolve you.
It is a hostile, dead rock. But what I find even more bizarre than the atmosphere is the sheer orbital mechanics of the planet, how it actually moves in space.
The rotation of Venus is highly anomalous compared to the rest of the solar system.
When you look at the raw numbers we have for its movement, it breaks your brain a little bit. Let us look at its orbit. Venus travels around the sun in a relatively circular path.
It takes 224.7 Earth days to complete one full orbit. So a Venusian year, the time it takes to go around the sun once, is roughly 225 days.
That is standard orbital mechanics. Closer to the sun, shorter year.
But then you look at its rotation. How long it takes the planet to spin exactly one time on its own axis. A single Venusian day.
It takes Venus 243 Earth days to complete one spin. A single day on Venus is physically longer than its entire year.
It takes longer for the planet to pirouette once in place than it does to run a full lap around the sun.
It is moving so incredibly sluggishly. And on top of that, it spins backwards.
Yes, the phenomenon of retrograde rotation. If you were to float high above the solar system looking down at the north poles of the planets, you would see that almost all of them, Earth, Mars, Jupiter, are spinning counterclockwise.
They all inherited that angular momentum from the swirling cloud of dust that originally formed the solar system.
But Venus spins clockwise.
Let us put ourselves on the surface for a second, just to visualize how alien this is. Let us pretend you are in an indestructible, heat-proof, pressure-proof suit.
And let us pretend a massive wind sweeps away the miles of opaque sulfuric acid clouds so you can actually see the sky.
If you stand on the surface of Venus, the sun would rise in the west.
And because the rotation is so agonizingly slow, the sunrise wouldn't be a quick event. The sun would breach the western horizon and then very, very slowly drag its way across the sky for months on end.
After more than 100 Earth days of continuous baking daylight, it would finally sink below the eastern horizon, plunging you into months of continuous, unbroken night.
It makes you wonder why. Why is it spinning backwards so slowly? Did something hit it?
That is one of the leading hypotheses. In the chaotic early days of the solar system, a massive planetesimal, a rock the size of Mars or larger, could have violently collided with Venus.
The sheer kinetic force of that impact could have acted like a brake, stopping its natural counterclockwise spin and knocking it into a slow, reverse clockwise rotation.
Another theory I have seen suggests it is actually the atmosphere's fault. That crushing, incredibly dense atmosphere acts like a heavy blanket.
The sun's gravity pulls on that thick atmosphere, creating immense tidal friction that, over billions of years, acted like a brake pad against the planet's rotation, slowing it to a crawl and eventually dragging it backward.
Both are plausible mechanisms. But regardless of the cause, Venus stands as a stark reminder of the chaotic fragility of planetary environments.
You can have a planet that is fundamentally identical to Earth in size and composition, but a divergence in atmospheric evolution turns one into a thriving biosphere and the other into a toxic, crushing hellscape.
Venus shows us planetary physics at its most extreme. It shows us what happens to a planet. But what happens to the star itself?
What happens to the massive roaring nuclear furnace that these planets orbit when it finally runs out of fuel?
Because stars do not live forever. And when a star like our sun dies, it doesn't just quietly dim like a burnt-out light bulb. It creates what I believe is the most spectacular, breathtaking visual art in the entire cosmos.
We are moving from the realm of planetary science into stellar evolution, specifically the endgame for medium-mass stars, the phenomenon known as the planetary nebula.
Now, before we describe what these look like, we absolutely have to clarify the name, because planetary nebula is one of the worst, most misleading misnomers in all of science.
It is entirely a historical accident. In the 1780s, the great astronomer William Herschel, who had just recently discovered the planet Uranus, was sweeping the sky with his reflecting telescope.
He kept finding these faint, fuzzy, circular patches of light glowing in the dark.
Because the optics of the time were still somewhat primitive, these fuzzy disks looked visually very similar to the pale, greenish disk of Uranus.
So his brain made a visual connection. He saw a round, fuzzy thing. It looked like the round, fuzzy planet he just found, so he labeled them planetary nebulas.
Exactly. He assumed they might be newly forming planets or fluid envelopes surrounding stars, but the name stuck. Today, we know with absolute certainty that planetary nebulas have absolutely nothing to do with planets. They are not planets, they are not making planets.
What they actually are is a gravesite. They're the magnificent, expanding, glowing clouds of gas that have been violently ejected by a dying star.
And to understand how a star ejects that gas, we have to look at the delicate balancing act that is a star's life. A star is not a solid object. It is a massive sphere of plasma held together by its own immense gravity.
For billions of years, gravity is constantly, relentlessly trying to crush the star inward upon itself.
But the star doesn't collapse because it is fighting back. Deep in the core, the immense pressure and heat cause hydrogen atoms to smash together and fuse into helium.
That nuclear fusion releases an unbelievable amount of outward pushing energy. So you have gravity pushing in and nuclear fusion pushing out.
This state of balance is called hydrostatic equilibrium. As long as the star has hydrogen fuel to burn, the forces are balanced and the star is stable. This is where our sun is right now.
But a star has a finite amount of fuel. Planetary nebulas are the fate of any medium-sized stars ranging from a fraction of our sun's mass up to about 8 times the mass of our sun.
When that core runs out of hydrogen, the outward push stops. Gravity instantly starts winning. The core begins to collapse.
And as it collapses, it gets hotter and denser until it gets so hot that it can start fusing the ash. It starts fusing helium into carbon and oxygen. This gives the star a temporary burst of new energy.
But the process is highly unstable. As the core burns this heavier fuel, the outer layers of the star react dramatically. The star expands massively, swelling up to hundreds of times its original size.
It becomes a red giant. If our sun becomes a red giant, it will swell so large it will literally swallow Mercury, Venus, and likely Earth.
But that red giant phase cannot last. Eventually, the helium runs out too. The core shrinks down into a tiny, ultra-dense, glowing hot sphere. But what happens to all that swollen outer gas? The core's gravity is no longer strong enough to hold on to it.
The star essentially shrugs. In a series of powerful thermal pulses, the dying star forcibly ejects its outer layers. It physically puffs its own atmosphere out into the vacuum of space.
The star sheds its skin, leaving only the naked, boiling hot core behind.
And that naked core is emitting fierce, high-energy ultraviolet radiation. That invisible UV light streaks out, hits the expanding shell of discarded gas, and excites the atoms, causing them to fluoresce.
It lights the gas up like a cosmic neon sign. That glowing, expanding shell of gas is the planetary nebula.
And they are fleeting phenomena on a cosmic timescale. That gas is expanding outward at dozens of miles per second.
Within a few tens of thousands of years, which is a blink of an eye compared to a star's billion-year lifespan, the gas dissipates into the interstellar void, thinning out until it becomes completely invisible.
Which explains why they are so rare. You have to catch a dying star at the exact right microsecond of cosmic history to see the nebula glowing.
Our optical survey suggests there are only about 1,500 planetary nebulas currently visible in the entire Milky Way galaxy, 1,500 out of hundreds of billions of stars.
It is like wandering through a massive silent forest and trying to spot a single firefly mid-flash.
But when we do spot them, and we point instruments like the Hubble Space Telescope at them, the visual morphology is breathtaking.
Let us paint an audio picture of a few of these, because they do not just look like uniform bubbles. Let us look at the Cat's Eye Nebula, located in the constellation Draco.
It is relatively young, maybe 1,000 years since the star puffed off its gas. But it is not a simple sphere. It looks like an intensely complex, unblinking cosmic eye.
It has multiple concentric rings of gas stacked inside each other and crisscrossing knots and loops of glowing material.
Or the famous Ring Nebula in the constellation Lyra. This one is easily visible with a backyard telescope. It looks exactly like a perfectly formed, glowing smoke ring drifting against the black velvet of space.
And the Hubble images reveal that the brilliant colors in these nebulas aren't just for show. They are a precise chemical map of the star's guts.
The gas that was mostly the star's outer atmosphere is primarily hydrogen, and when UV light hits hydrogen, it glows a vivid, deep crimson red.
But the heavier elements, the elements the star spent billions of years forging deep in its core before it died, like oxygen and nitrogen, those show up glowing in brilliant, piercing greens and blues.
You are literally looking at the freshly manufactured heavy elements that will eventually drift through space to form new planets or maybe new biology.
The diversity of shapes is what fascinates astrophysicists the most. As you noted with the cat's eye, they aren't all simple spheres. The geometry can be astoundingly complex, and that geometry is entirely dictated by the invisible physics happening at the very center, right at the dying core.
Which brings us to Minkowski 2-9, the Butterfly Nebula. This object is located roughly 2,100 light-years away from Earth. It is about 1,200 years old.
If you look at an optical image of it, the name makes perfect sense. It does not look like a ring or an eye. It looks exactly like a massive, glowing celestial hourglass or a butterfly with two enormous, delicate, fiery wings spread wide open across the darkness.
The shape is highly specific, and it tells a violent story. A spherical star should theoretically blow off its gas equally in all directions, creating a round bubble. To create a butterfly shape, something must be physically blocking the gas from expanding at the equator, forcing it to squirt out exclusively from the north and south poles.
And astronomers know what the blocker is. The dying core in Minkowski 2-9 isn't dying alone. It is part of a binary star system. It has a companion star orbiting extremely close to it.
As the primary star died and swelled up and eventually puffed off its outer layers, its naked core, which has immense gravity, began gravitationally interacting with its surviving companion. The dead core is actually stripping material off the living star.
A cosmic parasite.
Exactly. That stolen stellar material spirals down toward the dead core, forming a thick, incredibly dense, swirling disk of gas and dust right around the dead star's equator. The secretion disk acts like an impenetrable corset, or the nozzle of a hose.
So when the dead core releases its remaining energy, the stellar wind tries to push outward, but it slams into that dense disk of stolen material at the equator. The gas cannot go left or right. It follows the path of least resistance. It deflects violently upward and downward, channeled by intense magnetic fields shooting out from the poles of the star.
Creating the two massive wings of the butterfly, and the velocity of this gas is terrifying. Those two massive jets of glowing stellar material are streaming out into the vacuum of space at over 200 miles per second. That is over 300 kilometers per second. It is a violent, unimaginably powerful jet of plasma shaping the interstellar medium.
It is a gorgeous display of extreme mechanics. But if we strip away the expanding gas, if we look past the glowing green oxygen and the red hydrogen wings,
Yeah.
what is actually powering this entire display? We keep talking about the naked dying core that got left behind when the star puffed its layers away. What is that core?
That core is the ultimate endpoint of our journey today. It is a white dwarf.
The crushed, glowing ember of a dead star. Let us look at the terrifying reality of white dwarfs. When the red giant breathes its last breath and sheds its skin, the white dwarf is what is exposed at the dead center of the nebula.
A white dwarf is a dead object. There is no nuclear fusion happening within it anymore. The fire has gone out. It is essentially a sphere composed entirely of the heavy ash left over from the star's active life, mostly densely packed carbon and oxygen.
And because there is no fusion pushing outward anymore, gravity finally, completely wins the billions of years-long war. The core collapses in on itself with unchecked ferocity. It crushes inward until the very atomic structure of the matter refuses to be squeezed any tighter.
To understand a white dwarf, you have to grapple with the concept of density on a scale that defies human intuition. During this final collapse, the core takes the entire mass of the star, a star that was likely over 1 million miles across, and crushes it down into a volume roughly the size of the planet Earth.
Let us reiterate that. You are taking an object with the mass of our entire sun, an object so massive if gravity holds the solar system together, and you are compressing it into a sphere the size of Earth.
The physical implications of packing that much mass into that little space are staggering. It relies on a quantum mechanical principle called electron degeneracy pressure. Gravity squeezes the carbon and oxygen atoms so tightly together that the electrons orbiting the nuclei are physically stripped away. The core becomes a soup of nuclei swimming in a sea of highly compressed electrons. The Pauli exclusion principle states that these electrons cannot occupy the same quantum state. They physically resist being squeezed any closer together. That quantum resistance, electron degeneracy pressure, is the only thing stopping the star from collapsing further.
The resulting material is something that does not and cannot exist on Earth. It is 1,000,000 times denser than liquid water. 1,000,000 times.
Which brings us back to your initial analogy.
Yes. If you could somehow fly a heavily shielded spaceship to a white dwarf, scoop up a tiny sample of the material, and fill a standard pocket-sized matchbox with it, that tiny cardboard box would weigh as much as a fully grown adult elephant.
And the gravitational pull on the surface of this object is equally incomprehensible. Because you have the mass of a star packed into the radius of a planet, the surface gravity is hundreds of thousands of times stronger than what we experience on Earth.
If you, a human being, could somehow miraculously stand on the surface of a white dwarf without instantly vaporizing, you wouldn't just feel heavy. The gravity would pull on your body with such extreme force that you would weigh approximately 600 tons. You wouldn't even have time to register the sensation. Your skeletal structure, your cells, your entire body would be instantaneously crushed flat against the surface in a microsecond, spread out into a microscopic paste.
And you mentioned vaporizing. While a white dwarf is dead and no longer generating new energy, it is born from the collapsing core of a star. It starts its unlife unimaginably hot. The exposed surface of a newly formed white dwarf can reach temperatures of 180,000 degrees Fahrenheit or 100,000 degrees Celsius.
Which is exactly why it emits that fierce ultraviolet radiation that lights up the planetary nebula. It is radiating away its residual heat.
Correct. But because it has no internal fuel, it is just a cooling ember. It spends the rest of eternity, billions upon billions of years, slowly radiating that leftover heat away into the void. On the Hertzsprung-Russell diagram, which astronomers use to map the life cycle of stars based on temperature and luminosity, white dwarfs drop down into the extreme bottom left corner, very small, but very hot. Over billions of years, they slowly slide down and to the right on the graph as they cool and dim, fading from brilliant white to yellow to red until eventually they will become completely cold, dead, invisible chunks of carbon floating in the dark, a black dwarf.
Though the universe isn't actually old enough yet for any white dwarf to have fully cooled into a black dwarf, they take tens of billions of years to cool down. But there's a catch to all of this. There's always a catch when you deal with extreme astrophysics. A white dwarf cannot just be any arbitrary size, can it? There is a strict, inescapable mathematical boundary to how much mass one of these dead stars can actually hold.
This is one of the most critical concepts in modern astrophysics, the Chandrasekhar limit. It was discovered in 1930 by the brilliant Indian-American theoretical physicist Subramanian Chandrasekhar.
And the lore behind this discovery is amazing. He figured out this fundamental law of the universe while he was just a 19-year-old student sitting on a boat traveling from India to England to study at Cambridge. He is literally just doing the math on a ship deck.
Yes. He was combining the newly established rules of quantum mechanics, specifically that electron degeneracy pressure we talked about, with Albert Einstein's theory of special relativity. Chandrasekhar calculated that electron degeneracy pressure is strong, but it is not infinitely strong. As you add more mass to a white dwarf, its gravity increases and it squeezes the electrons tighter. To resist that squeeze, the electrons have to move faster and faster.
Until they approach the speed of light.
Precisely. And relativity dictates that nothing with mass can reach the speed of light. Therefore, there must be a maximum mass that a white dwarf can possess before the inward crush of gravity completely overwhelms the quantum forces holding the electrons apart.
And that limit is incredibly specific. It is exactly 1.4 times the mass of our sun. A white dwarf cannot exceed 1.4 solar masses. It is a hard limit programmed into the physics of the universe.
If a white dwarf gains more mass than that 1.4 solar mass limit, the structural integrity of the matter catastrophically fails. The electrons are forcibly squeezed into the protons, neutralizing them into neutrons. The entire Earth-sized object loses its quantum support and violently collapses in on itself in a fraction of a second.
And it triggers one of the most violent explosions in the universe, a Type 1, a supernova. The entire star is obliterated, and what is left behind, if anything, is an even more extreme object. A neutron star, which is essentially a giant atomic nucleus the size of a small city. Or, if the mass was high enough, the collapse doesn't stop at all. It punches a hole straight through space-time and collapses completely out of the observable universe, becoming a black hole.
The Chandrasekhar limit dictates the ultimate fate of these extreme objects. It is the dividing line between a quietly cooling ember and a catastrophic cosmic detonation.
Okay, let us take a deep breath and bring this entire journey together. Because the scale of what we have covered today is immense. We started in 1609 with Galileo standing in the cold, looking through tiny, flawed pieces of curved glass, proving the Earth orbits the Sun, but confusing Saturn's rings for two weird ears.
We tracked the evolution of optics through Isaac Newton's toxic metal mirrors, all the way to the unbelievable precision of today's megatelescopes. The 26-foot Gemini mirrors, cast in spinning ovens and polished so flawlessly that an Earth-sized version would only have a 12-inch bump on its surface.
We looked at the sheer engineering defiance of the Keck telescope in Hawaii, fighting the Earth's shifting atmosphere by using active optics computers physically bending 36 segmented hexagonal mirrors 1,000 times finer than a human hair twice every second to cancel out the wind and gravity. We talked about spinning pools of liquid mercury acting as perfect mirrors.
We examined the triumphs of the Hubble Space Telescope, escaping the atmosphere entirely, utilizing the conservation of angular momentum via reaction wheels to silently target distant galaxies. We saw how a microscopic flaw in its mirror was elegantly solved by astronauts installing corrective lenses in the vacuum of space, revealing supermassive black holes and an accelerating universe.
We discussed how infrared telescopes like IRS and JWST pierce through dense cosmic dust by observing the universe's thermal glow, requiring them to hide behind massive sun shields or bathe in liquid helium. And we used all those accumulated tools to peer out into the dark. We looked right next door at Venus, our toxic, twisted sister planet, a world where a runaway carbon dioxide greenhouse effect traps infrared heat, creating a lead-melting, crushing hellscape where the sun rises in the west and a single day drags on longer than the entire year.
And we journeyed deeper to witness the death of medium-sized stars. The planetary nebulas, William Herschel's historical misnomer for the fleeting, incredibly beautiful glowing clouds of stellar gas puffed off by a dying red giant and illuminated by ultraviolet radiation.
We painted an audio picture of the Cat's Eye in the Ring Nebula, tracing the green oxygen and red hydrogen. We marveled at the violent 200-mile-per-second jets of the Butterfly Nebula, carved by an accretion disk. And finally, we looked at the dead hearts powering those magnificent nebulas, the white dwarfs. An object the size of the Earth with the mass of the Sun, held up only by quantum pressure, where a tiny matchbox weighs as much as an elephant, locked forever under the strict, inescapable physical law of the Chandrasekhar limit of 1.4 solar masses.
It is a profound reminder that every time you look up at the night sky, you aren't just looking at a static, peaceful painting of twinkling lights. You are looking at a highly dynamic, incredibly violent, and endlessly fascinating laboratory of extreme physics. Every pinprick of light is a data point in a grand cosmic equation.
But I want to leave you with one final provocative thought to mull over. Let us pull two specific pieces of today's deep dive together into one chilling cosmic what if.
Oh.
We talked about the stunning butterfly nebula Minkowski 2-9, and we noted that the reason it has those two massive glowing wings of gas is because the white dwarf at the center is part of a binary system. It is a parasite. It is actively using its massive gravity to pull material off its surviving companion star, forming an accretion disk.
It is actively stealing mass.
Right. It is gorging itself on stolen gas. And we also just learned from a 19-year-old Subramanian Chandrasekhar on a boat that if a white dwarf steals enough mass to cross that magical threshold, exactly 1.4 times the mass of our sun, it can no longer support itself. Its quantum structure will fail. It will violently collapse into a neutron star or a black hole in a supernova explosion.
The physics of that limit are absolute and inescapable.
So think about this. As we use our giant 26-foot mirrors and our orbiting space telescopes to admire the delicate, colorful, glowing beauty of that cosmic butterfly, could we actually be watching a ticking time bomb? Could that unseen, parasitic white dwarf at the center eventually gorge itself on so much stolen gas from its companion that it tips past the Chandrasekhar limit? Could it suddenly, violently collapse and detonate into a supernova right before our telescopic eyes? It is something to deeply ponder the next time you step outside in the dark, look up at the stars, and capture a little bit of ancient light. Thank you for joining us on this deep dive. Keep exploring.